Okay, let's do another lecture on constrained maxima and minima. Okay, let's go ahead and find the stationary points. Cap f of xy, so this is our, what? This is our objective function, so I should maybe call that z. Okay. That's negative x squared plus 2xy plus y squared, and then it's subject to this constraint here. Okay, subject to this constraint. This is actually ends up being an ellipse. Okay, so we've got some sort of quadric surface, right? Okay, all right, hyperboloid of some kind, right? And then it's what? Subject to the constraint that the points lie on this ellipse. And I want to find the high and low points on that. Again, I haven't illustrated a second derivative test. Most books don't. Okay, but I did do that on my PowerPoint presentation if you'd like to take a look at it. Let's just talk about finding the stationary points though. Okay, I'm going to use the cross product method. Okay, let's find the gradient of cap f first. Let's go differentiate with respect to x first, then we would get what? Negative 2x plus 2y. Okay, and then comma, so we now differentiate with respect to y, and we would get what? 2x plus 2y. Cool. Okay, the gradient of little f. Okay, so I'll make my little f being that, the x squared plus y squared minus 2y, and 4 will be my c, okay, from my level curve there. Okay, the gradient, so that would be what? 2x, 2y minus 2, okay? And then I'm going to go ahead, like we did in the previous video, I'm just going to take the cross product of those two in the particularly short form, since I'm just dealing with 2 dimensions here. I'm going to talk about just the determinant of that 2 by 2 matrix, okay? So I just took the components there and put them into that determinant. I'm setting it to 0 like I should. And this is what you do. You know how to find that determinant. Okay, so the product of the main diagonal elements minus the product of the off diagonal elements, and set that to 0. That's what I did there. And I factored out a couple 2 factors here. So we get this, and jimmied around with some algebra till I finally got down to this. Okay, so I wrote it in descending order here with x's before y's. Negative x squared plus y squared, there's actually minus 2xy plus x minus y, and that's equal to 0. Okay, now that gives a relationship between the x and y here. Okay, and I've written that again here. And then I also need to reintroduce my what? My constraint. Okay, all right. My constraint was that it lay on this particular ellipse. So you see I've got 2 equations and 2 unknowns I need to solve. Now, this may not be quite so bad, but let me show you what you can certainly imagine situations where this is pretty gnarly, right? Okay, where this is pretty gnarly. And I'm not going to always give you ones that are just so you can use Lagrange multipliers easily. Rather, unlike the book quite often, and many books, instead I'm going to go ahead and have you use some technology on this, okay? Now, our arguments may not be perfect using the technology, but this is what I would like you to do, and they're not exact solutions, they're just numerical, at least in many cases. What I actually did to solve this problem is I took these two and graphed them on Desmos, okay? Just literally graph them together on Desmos and try that. And you will see on Desmos, I don't know if I've done this for you before, but on Desmos, what you can do is find the intersection of 2 graphs very easily, and you'll see it'll pick those points right for you. All you have to do is come over there and go click on them, and it will give you the coordinates of the point. If you want more decimal places, I think it only goes to like 4 decimal points, unfortunately. More or decimal places, go ahead and zoom in. Okay, so zoom in on the points, and you will at least get some coordinates for some pretty good points of intersection of these two. So that's what I did. Okay, so I didn't try to mess around with a bunch of algebra or anything like that. I just did it numerically. We might as well take advantage of our technology here. Okay? And I found these 4 points of intersection. Okay? So these would be the 4 stationary points. Now what I actually did was, what I was going to do was actually evaluate these, and I didn't because I'm too lazy. No, I just forgot to do it actually. I don't know what those values are. But you might actually evaluate the function f at these various points. And because we're doing a nice closed curve, a compact curve here, you would just go through these and find the maximum values and the minimum values, and you would be in pretty good shape for where the high and low points almost certainly are. Okay, there's a little bit of ambiguity with regard to what would correspond to a saddle point, but there it is, or more like an inflection point is more what it's like. Okay, but don't be afraid on these to use some technology. Okay, all right, very nice. Let's talk about a different problem here. A container in the shape of an open rectangular box has a fixed volume. Okay, its volume is supposed to be 12 cubic meters. The material used for the bottom of the container costs $3 per square meter. Material for the sides, only $1 per square meter. What dimensions will minimize the cost? Okay, what's going to be the cost of this thing? Okay, well, let's see if I've drawn a picture. I did. Okay, so I've got these dimensions, x, y, and z, kind of appropriately. Okay, so we need to go through here and let's see, the area of the bottom, the base we'll call it, is x times y, so the cost is 3 times xy. Okay, so that's 3xy. So that would be the cost for the base, since that's what, $3 per square meter. So this is in terms of dollars. Okay, now on the sides here, I've got what, an xz side, and I've actually got 2 of those, and those are $1 per square meter, so I've got 2xy for the cost here. Likewise, I've got 2yz for the cost of these sides. Okay, now this is a relationship here, and we've got this constraint that x times y times z has to be 12. Now there's also a implicit constraint that x, y, and z have to be non-negative. Okay, positive even. You want an actual box. Okay, so this is explicit here, and this is kind of implicit here. I'm going to throw it in though. Okay, so do you see what we're doing? We're trying to find the minimum value of c subject to that little condition there. So my little f of x, y, z is x times y times z. And my c here, my constant c from the previous lecture, is 12. My cap c here is cost. That's this function, 3xy plus 2xz plus 2yz. Okay? Okay, I'm showing you this because we're going to be using our cross product method on this rather than trying to use Lagrange multipliers. Okay, so I found the gradient of my c, and this is it. 3y plus 2z, 3x plus 2z, 2x plus 2y, and then the gradient of little f. Okay, not too bad. Okay, yz, xz, xy. I want the cross product of these to be 0. Okay, all right, if you can, I, j, k, if you like 3 by 3 determinants. This is a notation actually created by students earlier. But you take the cross product of these and you get this ugly thing. Okay, you get that ugly thing. So you've got what? The 3 terms there, algebraic. Okay, and it actually cleans up a little bit here, fortunately. It becomes 3x squared y minus 2x squared z, 2y squared z minus 3xy squared, 2xz squared minus 2yz squared, and you want to set that equal to the 0 vector, right? So 0, 0, 0. Okay? Okay, so that means each one of these, we've got 3 equations and 3 unknowns here. Okay? This is not going to be something you can solve in Desmos. So hopefully there will be a way around this, right? You might be able to solve it on something else. Okay, maybe Wolfram Alpha, maybe GeoGebra even, but probably not. Okay, I'm going to notice that I can actually kick out x squared from the first one, so I'm factoring it, y squared from the second, and 2z squared from the third. Now, notice that x squared, y squared, z squared, these are all, what, non-zero numbers. They're, in fact, positive numbers. I'm just going to divide them out, okay? We know from our constraints that we're not allowed to have those to be zero. That wouldn't give you a box. It wouldn't give you a container. Okay? So in fact, our constraints boil down to this instead. 3 linear equations and 3 unknowns. That's a 2 there, by the way, not a z. I crossed my z's. Okay? All right? Now, if you actually work these out, you're going to find one of them is redundant. Okay? So you're going to take any 2 of them that you like. Okay? I took these two. These 2 together imply the one at the top. Okay? Actually, any 2 imply the other one. But this one is redundant. So I mean, literally, we're just going to ignore that because these 2 imply this. Well, that would mean there's infinitely many solutions then. Well, no. Again, this is only, all we're working on is this constraint right here. That thing. Remember that we got that by what? Differentiating with respect to arc length and stuff originally. And that was all theoretical. We never actually parameterized with S because it's typically too hard. So what we had to do was what? In the end, reintroduce the constraint. Okay? So now I have these 2. Those are acting like constraints now, I guess you could say. And then I've got my original constraint. Okay? All right? So I've got x is equal to y. So I wrote everything in terms of x. Okay? So x is equal to x, obviously. Y is equal to x. And z equals 3/2 x. So I put those all together, and I've got a single equation and a single unknown. And it turns out that x is 2. Okay, so that means 2 meters. Remember, y is also going to have the same measurement, so y and x are equal, so that's going to be 2. Meanwhile, z is going to be 3/2 as much. So there we go. So z, if you like the British, is 3. Okay? Alrighty. Well, there you go. There's some examples together with the PowerPoint presentation in your reading. It should be pretty good. Okay? All right. Hope you understood.